Okie dokie. Artichoke. I'm getting some different colors here. All right. Okay. Oh, you can't see those, can you? Well, I'll have to turn you. There we go. Yeah. Okay, over here on the board, I listed some what are called strong acids. There are only a few strong acids, but you got to know them. If you don't know them, you're going to be a mess for the next several times we meet. So here are the strong acids. Okay. This one's called perchloric. I'm going to erase these words because I'm going to need room. So write them down. Are you writing? Are you writing? Okay. This one's called nitric. And most of these you have probably heard of. You might not have heard of perchloric. Nitric acid. This is sulfuric acid. Sulfuric acid. Car battery acid. Okay, it's using car batteries. Nasty stuff when you put water in it. Do as you order, add acid to water. Do it the other way around and sulfuric, nasty. Hydrochloric, you've heard of hydrochloric acid. Hydrochloric. Then you have, I hope you noticed something, Cl, Br, and I are all halogens. Okay, those are all halogens. These are the halogen acids. Hydrochloric, hydrobromic, that should be a little b, all one word, and then iodic. Some of you might say, hey, what about HF, hydrofluoric? You're leaving out the hydrofluoric. Hydrofluoric is actually a weak acid. What makes strong acid a strong acid? And then why is hydrofluoric weak? Bottom line, these ionize 100%. So if you were to take hydrogen chloride, which is a gas at room temperature, and you put it into water, dissolves in water, and it separates, breaks down, ionizes 100%. Every single hydrogen will go boop and leave the chlorine. That's what makes a strong acid. So every single hydrogen comes off of that. Every single hydrogen comes off this when you mix it in water. 100% ionized. The first of the two of every single hydrogen comes off the sulfuric acid. The second one does not. That's interesting. We'll go through that when we do our, we do have to do a quadratic. I warned you about that. We have to do a quadratic. And we'll do it because of this one here and the two hydrogens. That's a diprotic as opposed to these monoprotic acids. And so every single hydrogen comes off when you put this in water, every single one. Now, if we have a weak acid, which is hydrofluoric, there's so many weak acids, and we'll be going through all kinds of them. Even today we'll go through some weak acids. Then what you have is not all the hydrogens come off. Some do. Some do. And these can ionize anywhere from point-something% to up to maybe 5%. And when they do that, only 5% of the hydrogens come off. Well, then it's a weak acid. That means 95% of the hydrogens do not. That makes a weak acid. Now, here's the thing. It's a weak acid because of a strong bond. But fluorine really likes that hydrogen and doesn't really want to give it up very much. It's like, no, I really don't want to give it up. No. Strong bond makes weak acid. All right. Okay, so I am going to take these names, and some of you might be saying, well, what about bases? What about bases? What about the bases? What makes a strong base versus a weak base, right? Good question. Good question, Billy. Good question. All right, well, here's the thing. If you're 1 and 2, if you're OH, you're hydroxide. So it has to have hydroxide. It has to be a traditional Arrhenius definition base to be a strong base, and the metal attached to the OH has to be out of group 1 or 2. So it can have OH and not necessarily be strong. If it doesn't have OH, then it's never strong. It's a weak base. But if it has OH, it can be strong, and it can be a strong base if the metal is out of group 1 or group 2. Example, sodium hydroxide. All right, out of group 1. What about calcium? Calcium hydroxide. Calcium out of group 2. Okay, this is your alkali metals, your alkali group, and your alkali earth metals, alkaline earth metals. Those give you strong bases when attached to the OH. So that's how we define strong bases. Got to have an OH and got to have that metal in a group 1 or group 2. If you don't have an OH, or if you have an OH attached to something else like lead, if you had lead hydroxide, lead's way over here on the periodic table on the right, then that would be a weak base. Okay, so we got that out of the way. We'll come back to that a lot. You got to know. You just got to. Because I will say, well, we have to do an equilibrium problem with this acid. And remember, equilibrium only occurs with acids. You actually don't remember, you learn that equilibrium only occurs with acids if you have a weak acid or a weak base. So you might say, well, how do I know I'm going to do equilibrium? Because you have a weak acid. Well, how am I going to know it's a weak acid? It's not one of those. That's the answer. If the acid is not one of these, it is like the Ukraine. It is weak. The Ukraine is not weak. The Ukraine is weak. Seinfeld. Check it out. All right. So let's, okay. Oh, okay. That's weak acids and bases. I'm looking at the clock here. I'm getting hungry. I gotta eat lunch. Let's do auto ionization in water. So let's look at the list. We got water-based properties, auto-ionization, K. Ooh, there's a K. Oh, we learned about Ks last week. KW, K for water. Let's go over that. Let's talk about water for a minute. H2O. So you've got H. Typically you're going to see water like this, or if you Lewis structure water, it's going to look like that. Okay, I'm going to draw water like this time. Because there you can see the hydrogen ion and the hydroxide ion. So water does something called self-ionization. It undergoes this self-ionization or auto-ionization, the same thing. So what does that mean? It means it breaks down. It will separate. Most water molecules, the vast majority of water molecules in your bottle of water. I have a bottle of water right here. Okay, bottle of water right here. Okay, there's some H2O, good old high quality, made in America H2O. And this stuff in here is that. But sometimes water does this. Separates. They go through a divorce. I don't want to be with you anymore. Fine. Okay, fine. And they're hanging out here. Now water does that. Doesn't do very much, but it does do that. So therefore, because it doesn't do that very much, but it does do that, I'm going to draw a little equation for it. You have HOH does this. Back and forth. That means it can break down, but it will also go back. Now, if we were to do a K value for this, I talked about water in the K value videos. The K value for water breaking down into that is really small because it doesn't want to do that, but it does, but not just very much. So K value for water, if you have 1 molar concentration, normal conditions, there's a K value for water, and you guessed it, it is very small. Okay, we'll get to that in just a second. So this goes to this goes back to this, so you get a vast majority of this, a little bit of this, so in this case, certainly the product or the reactants are favored, the way I've got it written here. And the K value is small. So the KW, the K value for water is 1 times 10 to the negative 14. Okay, that's the K value for water. Small number, right? Makes sense. Water doesn't like to break down into this, so it should be a small number, and it is. All right, now, one other thing. Let's say the water does, you got water, you got your bottle of water. Here there's a little bit of hydrogen and hydroxide ions in there floating around. Well, what do? They balance each other out, don't they? Sure they do. Because every water that breaks down into this and this is one of each. What's the pH of water? You know something about pH, you do. Okay, you do. pH means the power of hydrogen, and there's a scale for it. And I bet you, most of you, at least know that the typical scale for pH is 0 to 14. 0 to 14. Oh, is that just a coincidence? There's a 14 here, and there's a 14 here for the kW for water? No, it is not a coincidence at all. Okay. In fact, let's say that we got some water, some of it separates out like this, and you dump something else into the water. You add something into the water, okay, like ammonia. Remember ammonia? So I just dumped some of this in the water. There's a hydrogen due to the auto-ionization, the self-ionization. It's sitting there and goes, hey, oh, thanks, man. Now what do you have? You have more OH floating around in the water. It can't pair back up with this hydrogen because it got sucked up by the ammonia. So what are you left with? You're left with OH floating around. What is that? That's basic. So not to get too much into how all this chemistry works right now, but the bottom line is if you have auto-ionization, you have H's and OH's floating around, and you add something to suck up one of those, you're left with the other one. That's basic. This would be a basic solution. We've changed the pH. We don't have just basic neutral water. Basic neutral. We don't have neutral water anymore. We have basic solution. We added ammonia, which would make sense. If you add ammonia to water, it should become basic. Now, the chemistry behind why it does might be a little confusing at this point, but that's okay. If you don't get this, that's okay right now. But if I add ammonia, which is a base, to water, I should get a basic solution. It just makes sense. The chemistry is because this thing goes in and it grabs a hydrogen from the self-auto-ization process, grabs one, sucks it up, takes it away, and you're left with this guy floating around. Hey, buddy. But you made the solution basic. Oh, okay, I did something. See? All right, let's see. So let's go back to my hydrogen and my hydroxide floating around in solution. Okay, you're with me? Let's say you dump in some acid. And maybe that acid is, well, let's go with the strong acid. Let's go with one of these. Let's go with hydrochloric. You drop in some hydrochloric acid. You put that in the water. Plop, plop, fizz, fizz. Oh, what a really fit is. You watched that video, I hope. I went on the lab. I hope you did that. Thank you. This separates, adds more hydrogen. You got chlorine floating around, but that doesn't do anything. That has no effect on acid and base. It's not a hydrogen or hydroxide. So it just kind of goes, bleh. This adds some of those. You have more of those than those. What are you going to have? You're going to have an acidic solution. Sure are. So that's a little bit of acid-base chemistry. We're going to certainly get into a lot more, but let's just go over now for this video, just end this with focusing back on this right here. This KW is really important because here's why, and here is the bottom line. If you stuck around this long for this video, you have done yourself a favor because this is hugely important for you. You ready? The concentration of hydrogen. And remember, square brackets mean concentration, the molar concentration of hydrogen and hydroxide in good old basic water. These two together will equal 1 times 10 to the negative 14th molar. That means moles per liter. All right, so this means that these concentrations are going to total this number, and they'll do that every single time. Because what happens is in a neutral solution, you have your water and it separates. So together they've got to equal this. So how much of each of those are you going to have? You'll have 1 times 10 to the negative 7 and 1 times 10 to the negative 7. And you're multiplying these, so you multiply exponents, you get 14, right? So we have this amount of this and this amount of this in good old high quality made in America neutral water. That is important to solve the problems that we're going to about to delve into. So what happens then? What happens if you start adding something to the solution that takes away some hydrogen? Well, what happens is this concentration has to go up. If you go down on one of these, the other one will have to go up. So, because water is always self-ionizing, it goes hydrogen, hydroxide, hydrogen, hydroxide, hydrogen, hydroxide, hydrogen, hydroxide. So if you start taking away a few of those hydrogens, grab a hydrogen, grab a hydrogen. So you got a hydrogen hydroxide, hydrogen's gone. Hydrogen hydroxide, hydrogen's gone. Hydrogen hydroxide. All right, that one's not gone. So what just happened? You've got 3 hydroxides in 1 hydrogen. So your ratio is changed to 3 to 1 instead of being 1 to 1. Bottom line, if that doesn't make sense to you, here's what you need to know. You look like this is what you look like. That's you. You're a bottom line kind of person. Bottom lines. And I circled the bottom one because that's. Bottom line is, remember that these 2 values, your hydroxide concentration and your hydrogen concentration, always will total to be 1 times 10 to the negative 14th in your water solution. All right, we will come back to that in the next video by doing some problem solving. And maybe the problem solving, if you don't quite get that, that's okay. Maybe it's the first time you've ever heard this, so it takes a little while to get used to. Rewind, or wait till the next video. We'll do some problems, and hopefully you'll be able to see how the chemistry works. If you don't yet. Okay, see you soon. Taking a water break.